Hello everyone and welcome to lecture 46, which is about designing with op amps. And in this lecture, we want to look at the four basic circuits which have been covered in previous lectures and just think about how we can design and apply them in bigger and more complex circuits. So we've already talked about one in some detail, and that's the follower, the voltage follower, which, if you recall, is going to be the case where if I apply an input to my positive terminal and have a feedback going to the negative terminal, the inverting input, whatever this input is, it's going to, the output will deliberately try to balance out this input, so it'll output 6 volts and give me 6 volts there to balance it out. And if I change that to 7, it will update accordingly. And that's useful for interfacing, and it's useful for if I'm going from a stage of an amplifier that's low current to one that's higher current, you would want a voltage follower in that situation potentially. Let's now look at the comparator circuit. So the comparator, if you remember, has no feedback. This is the open loop one without the closed feedback loop that drives it to balance to 0. And again, I do want to kind of go back and say that with negative feedback, the tendency is to drive to 0. So it's trying to zero things out on the input side. And the output will do whatever it needs to do to balance it out. So a way to think about that is like a thermostat. If the temperature gets too cold, the output of my heater will increase in order to balance that back out again. So the comparator, if you recall, is basically, I have two inputs. So if this is 4 and this is 3, and this has a source volt of 15 to minus 15, this will immediately be negative 15 because of the super high gain. So whichever one is bigger is going to determine what the output will be, and the output will immediately cause saturation. If we flip these two and make this 4 and this 3, it'll change it to a positive 15. And we talked about how comparator circuits are super useful in a lot of digital applications where you just want to compare two inputs and pick which one is higher to do something else. But there's also an application in AC circuits. So you can see here, this is a basic comparator op amp setup. If I apply a ground and an AC input, the ground being at 0. Oh, you'll see it's going to oscillate between 15 and negative 15 volts. And it's not a smooth oscillation, it's going to be a more squared off oscillation. And you can see that also if I pull up the internals. For the 741, you can see the input voltage is a sine wave and the output is a amplified square wave. And the input voltage here is going to the positive input terminal, the non-inverting one. So the square wave is in the same phase as the sine wave. So that's another application of the comparators. When you use AC, you are able to get a square wave out of it, which can be really useful in a lot of applications. We also learned about using negative feedback beyond just the voltage follower. So we learned inverting and non-inverting, and the difference is where you put the positive voltage. So is the positive, or you can really think about it, the difference is where is the ground? Is the ground at the inverting or the non-inverting? So remember, with an inverting, the gain is going to be minus R2 over R1. With a non-inverting, the gain is going to be R2 over R1 plus 1. And the basic setup is, if this is my minus and my positive, for both of these, we have our two resistors. R2 is always going to be this one, the one coming off of the output and feeding back into the inverting input. R1 is always going to be this one. The difference is, does R1 connect to a voltage, or is it connected to ground, and is this connected to the voltage? So with this in mind, we can set things up a lot of different ways. So there's different reasons why we would use one or the other. So the main one, or maybe not the main one, but a main one is, do we care if it inverts or doesn't invert? So with AC electricity, it may not really matter that it inverts our signal, because it's really going to behave the same way. If it's just the opposite, it doesn't really impact much. So that can be a really useful way if I want to get an amplification that's between 0 and 1, so less than 1. There also might be cases where I want to get a negative voltage out of this with DC, and then you would obviously want to use inverting. Beyond that, for things that are greater than 1, you can really kind of use both of them, and it really kind of depends on whether you want it to, whether you care if it's going to be negative or not negative. So if I, for example, had a input and an output, let's say this is going to go from 15 volts to negative 15 volts, and I have my, this is for source, I should say that's the source being the DC power supply powering the op amp, and for inputs, I have V plus, V minus. If I want to have basically a 5-volt source and I want to double it, I can use my voltage divider to design that. So if I want to double this, which means I want an amplification of 10, remember that if I use an invert or a non-inverting amplifier, the formula is going to be R2 over R1 plus 1. So if I have a gain of 2 that I would like to achieve, that's going to be R2 over R1 plus 1, subtract 1 from both sides, and R2 over R1 has to equal 1, so R2 has to be the same as R1. So all that is to say, I can, if I have a non-inverting amplifier feedback loop and I want to double the voltage, all I need to do is pick two resistors that are equal to one another. So to design that, I just have my plus, my minus, my output. And remember, if it's non-inverting, this is going to go to the battery, which we said is 5 volts. And then we have our two resistors. And then this goes to ground. And this point goes back to the inverting input. So as long as they're the same, we will get 10 volts out. So I can make this 2K, I can make it 5K. It really will give me the same amplification either way, as long as they're the same. If I want to triple it, then R2 over R1 has to equal 2, because then 2 plus 1 would be 3. If I want a gain of 3, I'm always adding that plus 1 in per the equation, so R2 over R1 has to be 2. So again, R2 is the one that is here that connects back to the inverting feedback. So if I have 2K here and I want to triple it to get 15 volts, I need to make that 4K. If I wanted to do this with an inverting system, let's say I'm using AC, so I don't really care that it's going to do a phase shift on me because it'll be the same. I can use the formula that the gain is going to be equal to minus R2 over R1. So if I want to double it, then R2 over R1 has to be 2. So that means that R2 has to be twice as big as R1. So in my setup, I have my plus, my minus. Remember, in an inverting setup, this goes to ground. I have my output. The feedback loop is pretty much the same. Remember, it's going to try to drive this back to 0. Like, negative feedback drives to 0. It tries to balance everything out. This would go to my AC power supply, which also goes to ground. So if that's 40 hertz, let's say 10 volts, and I want to get 20 volts out, then I know that the ratio I need to achieve is 2. So I would pick like 2000 ohms for this resistor and 1000 at this resistor. And I would feel confident that I'm getting the amplification I want. So you can see this is a really cool thing because we have the ability to design our amplifier to give us the exact amplification we want. If I wanted to, I could make this a rheostat, a variable resistor, and that would give me the ability to toggle between voltages of different levels, so I could smoothly control it. So there's a lot of really cool opportunity, and we can really control amplification using negative feedback, and it's a much more intuitive way of doing it than designing it with transistors from scratch. So that is how we can start to design some really cool circuits using the basic fundamentals of op amps. In future lessons, we're going to learn about what happens when we use positive feedback and how to get oscillation out of an op amp, and then we'll move on to timers and voltage regulators.